Okay. Hello, everybody. Can everybody online hear me well?
Yes. Yes. Thank you.
I'll adjust this camera later when I go to Blackboard. And hello, everybody here in the classroom. Nice to see you again. Yesterday, it was only one person. So today is lecture number 4. And I think it's not that complicated lecture, primarily because it's just one topic. We talk about hurricanes. It's not split in multiple subtopics like last lectures. So here is a photograph of a hurricane from a satellite, Hurricane Katrina in 2005, the costliest ever hurricane in the United States. Over 125 billion in damage, some people say over 200 billion in damage. And really, as we will see in next lecture, tornadoes are systems that can form the strongest winds close to the planet. But tornadoes are very localized. They can destroy pretty much everything. Hurricanes perhaps do not create as strong winds as tornadoes, but they affect huge area. So they are maybe even more destructive in that sense. And they are more powerful than extratropical cyclones or mid-latitude cyclones that we covered in lecture number 2. But as we will see in a few slides, they're also smaller than extratropical cyclones. They do resemble similarities. You can see they rotate cyclonically, namely the counterclockwise direction. Here is Florida, the rest of the United States, and they have this characteristic eye of the storm, which we will discuss later. Here are some of the photographs associated with Hurricane Katrina. So you have flooding associated with storm surge that we will discuss. 90% of casualties in case of hurricanes comes from storm surge, not necessarily strong winds, and some damage caused to the environment and cars. Hurricane Harvey was, not sure, maybe the second costliest hurricane in the United States. Again, extensive flooding associated with storm surge. Here is Hurricane Andrew, snapshot from different points in time, how it is approaching Florida, passing over, and then traversing over there into Texas. And here is damage. As you can see, this is completely flattened, pretty much, community. So if you compare it to tornadoes, well, you cannot get worse damage than that. So from this point of view, damage is similar to that caused by tornadoes. Because if you destroy something, you cannot destroy it more than what is already destroyed. Here is a cyclone Idai from 2019 that hit Mozambique in East Africa, just west of Madagascar. Here is the extent of flooding and some of the pictures associated with this cyclone that caused a lot of damage and deaths. Now, how do we classify hurricanes? We classify them using Saffir-Simpson intensity scale, which is based on 1 minute maximum sustained wind speed, measured generally at 10 meters above ground. And we'll see this is profoundly different to tornadoes, where we use 3-second estimate. So hurricanes are classified between CAT, category 1, with entry 1 minute maximum wind speed is 33 meters per second, 2, 3, 4, 5 categories, wind speed is increasing. If a storm is strong, but not this strong, we call it tropical storm. Or if it is below 70 meters per second, but resembles cyclonic rotation in the tropics, we call it tropical depression. So what's the difference between tropical depression, tropical storm, and a hurricane? Nothing except intensity. And there's also minimum central pressure that is used in categorization. As you can see, as the wind speed is increasing, central pressure in the storm is decreasing, and some description of damage here. Now, here is a list of 10 deadliest. So also, hurricanes are called hurricanes in the Atlantic. They are called typhoons in the Western Pacific. And they're called cyclones actually in Indian region as well as Australia. So you have to be aware a little bit of that labeling, but at the end of the day, these are all same systems. So you can call it safely a tropical cyclone. Here are 10 deadliest tropical cyclones. Can somebody see some pattern in the table? So this
Bengal.
Yes. You can see, that's correct, that 6 out of 10 deadliest happen in Bangladesh. And there is reason for that. There are mainly 3 reasons for that. First of all, that Indian Ocean and Bay of Bengal over there is extremely hot water, the hottest water probably, one of the hottest waters in the oceans. And as we will see in this lecture, warm surface waters are prerequisite for hurricanes. So there is a lot of fuel in the ocean for hurricanes in that region, but that's not enough. Other reason is that Bangladesh has very, very high population density. It's like 200,000 people per square kilometer, something like that. So when a disaster happens, it's much more likely that more people will die than in some sparsely populated regions. And third reason, well, there are 4 reasons actually. Third reason is that the coastal area of Bangladesh is very fertile. So there's a lot of rice agriculture that is happening there, and many people tend to live there because of that's what their source of income. So there is very high population of people, particularly in regions close to the ocean. And then fourth reason is that the coastal protection system is not very well developed. So when the hurricane strikes, rather storm surge, it can penetrate deep into the coast, thereby injuring and killing a lot of people. So you see, it's a combination of many things that result in Bangladesh being particularly vulnerable. As I said, storm surges are the main issue when it comes to deaths associated with hurricanes. So that's a big wave or series of waves, a dome of water, if you want, that comes together with hurricane, impinges on the continent, and we call it storm surge. You can see here that some storm surges were 7 meters, 6 meters high, and this is just enormous. So you can see that think about this. In November 1917, in today's Bangladesh, one hurricane killed between 300,000 and 500,000 people. This is just mind-blowing number. A very famous hurricane is also Gulf hurricane in Texas that killed over 5,000 people in one day. That's the deadliest day in the history of the United States. Of course, more people died than in World War II or whatnot. But in a single day, nothing killed more people in the US than this hurricane that hit Texas. And the story said, I read, that of course, even at that time, people knew about hurricanes, but there was no, of course, satellites, radars. So you just out of nowhere, you get storm surge, and not out of nowhere, though. The weather is getting worse and worse, but you're hoping it's not going to be absolutely horrible. And in this day, it was horrible. But the story says that they actually had some sort of protection close to the coast. And they didn't have hurricanes for many, many years. And because that protection was obstructing view of the ocean, they decided to remove it and said, okay, there were no hurricanes for quite some time, let's just remove it. That's what I read, I don't know. And you see a few days or weeks after that, famous hurricane Galveston. And some other hurricanes you can see here. Particularly, we will check here in the next slide, Hurricane Haiyan, that in 2013 hit the Philippines. And here is an example of storm surge. I don't know why it is lagging. As Professor Burlando say, Windows. I don't know, but let me restart the slide. Maybe it's gonna work better. No, there is no fixing. But this is an example of storm surge, and this already looks bad, but the things will get much worse, as you will see. So you see, this is in the Philippines. This is actually the east part of the Philippines, so they call it typhoon there in Western Pacific. And here is already flooding that looks horrible, but this is storm surge. Now you can swim any way you want, freestyle, backstroke, you're not surviving this. Particularly, even if you can swim, imagine how much material is in that water. So unfortunately, in this case, over 6,000 people died in a storm surge. Okay, so hurricanes are extremely deadly, particularly storm surges. Now, as I said, they tend to form in the regions where we have very hot water. So the left figure here is average temperature on one particular day in August of 2001. And you will see that the warmest region is right next to equator, the tropical regions. And you can see that hurricanes tend not to form over here because it's cold. They don't form over here because it's cold. Famous Peruvian current. They do not form very high along the west coast of the United States because it's cold. So they typically tend to form over here and over here in this region. Now, as we will see, they never form right next to the equator because there is no Coriolis force at the equator. And as we will see, it is necessary to have at least a little bit of Coriolis force to form low pressure system, form cold circulation. And this is their typical motion. So that when we are talking about Atlantic, they typically form here in the east part of Atlantic, and then they move with so-called trade winds. I didn't have time to talk about general circulation of the atmosphere, but winds here are typically from east to west or northeast to southwest and so on. So they move like that, and then due to Coriolis force, they also curve. They end up entering the United States. They end up in westerlies. Westerlies are predominantly predominant winds in mid-latitudes, and then they make this curvature typically in the Atlantic. Another important feature about hurricanes, or at least important, one very recognizable feature is the eye of hurricane, which is pretty cloud-free region in the very center of the hurricane, usually about 50 to 65 kilometers in diameter. And around the eye, there is very deep layer of cumulus clouds, storms called the eye wall. This is where the strongest winds and most severe weather occurs. Now, in the eye of a hurricane, actually the weather is quite nice, as we will discuss soon on the blackboard. It's cloud-free, weather is nice if you are on the land. If you are on the ocean, beneath or around the eye of a hurricane, the sea is still very rough and just crazy. And two more slides. So this is the largest ever typhoon or hurricane tip that formed in the Pacific. Again, Pacific is warmer than Atlantic. The hurricanes that form there tend to be larger. This is the region of destructive winds in the red circle. This is approximate size of that hurricane compared to the United States. You see this is the United States. This is the largest hurricane in Atlantic, Hurricane Ike from 2008. And there is another one here, I don't know if you saw, Little Marco in 2008. This is the smallest hurricane ever. So you see, the largest hurricane in the Atlantic is just part of the United States. And that's really small compared to rather a normal extratropical cyclone that we checked in lecture number 2 that look much bigger. This is US. You see almost entire United States is covered by this mid-latitude cyclone. Okay. Any questions about this? Was just pictures introduction to lecture. So now stop sharing. I will disconnect, but I want to go at the very end of the lecture. I want to show you one more slide that I find fascinating. After we talk about formation of hurricanes and so on. Okay, so now video needs to be on. I need to adjust this camera. No, but I'm not. No. Oh. Okay. So no questions about this. Quite simple. So how hurricanes form? Okay, that's what we will first discuss. Well, there are 3 necessary ingredients or conditions that need to be specified for hurricanes to form. Number 1, there needs to be Coriolis force. Okay, so from observations, we know that hurricanes do not form within 5-degree latitude around the equator. So plus minus 5 degree, plus is north, minus is south. Degree latitude around the equator, there is no hurricanes because Coriolis force is too weak. You see, if you have a low pressure somewhere here, and you have air due to pressure gradient force moving in towards low pressure, you need a little bit of Coriolis force. So you get circulation, and then finally you establish some sort of circulation like that. So you get low pressure system in the center that can be maintained. Okay, if you don't have Coriolis force, then air rushes in and fills out this low pressure region, and that's it. You don't have sustained low pressure system. Okay, so first is Coriolis force. Second is SST, sea surface temperature, needs to be approximately more or less 26 degrees Celsius. Some books say 26.5, some books say 27, I don't know, let's say 26. In the first approximately 50 to 60 meter depth of the ocean. Okay, so the ocean needs to be very warm, but not first 5 centimeters of the ocean, but rather first 50, 60 meters, because as you will see, that hot water that evaporates is the main fuel for hurricanes. And 3 is low wind shear, particularly at higher elevations. So the winds should not vary much with height, because that tends to disorganize the convection in tropical regions. Okay, now these are from observations, people figured out these need to be satisfied. But it does not mean if these are satisfied, you will get hurricane. Are there any questions about these questions? Okay. So hurricanes form as some sort of storms in tropical region that come together and then form a kind of chain reaction, like a nuclear reactor. And I'll explain what that reaction is. When these storms are self-maintained and actually grow in intensity. I will tell you soon what can cause these storms to develop and come together to begin with. But let's just assume you do have a storm, and then I'll tell you how you get it. So let's say here is a ocean, height is Z. So let's say this is X direction. And let's say we have low pressure system over here, which means you are underneath storms. Let me put it here because, so you have low pressure system underneath the storms. Again, I'll tell you later how you get the storms. What will happen here in this case if you have low pressure system? First of all, if I would ask you, you have a low pressure system here, what does it mean? With respect to what?
To surroundings.
Exactly. So you should never say you have low pressure here with respect to somewhere above. Pressure always increases with height. Okay, there is no other way. So low pressure here means it's low pressure compared to same height, but somewhere radially away from that. So if you have low pressure here, you will have pressure gradient force moving the flow towards the low pressure. Okay? Now you have to keep in mind condition number 2. These are extremely warm oceans. So there is a lot of evaporation. This air is very rich with water, and evaporation just continues because the water is very warm. So this air that is spiraling in is very moist, and then it converges here, and you start having convection, like so. Now, as you have this convection, some clouds form, cumulus clouds, deep clouds. Now, what happens in clouds? Well, condensation happens. Condensation is release of latent heat, as we discussed many times. So, is this air in the cloud warmer or colder than the surrounding air? What do you think? It has to be warmer because of the latent heat release. And then at the top of the cloud, somewhere here, you have high pressure. Now, how do you get high pressure over here? There are 2 ways to explain it. One is kind of not so good way. One is to say, there is a tropopause here. You remember? This is top. By the way, tropopause in tropical regions, it's 18, 19, 20 kilometers above the ground. So this is very high. So you can say, this air hits the tropopause, it cannot go into stratosphere, so it will just spread. That's kind of poor argument, but maybe you can use it. And there is better argument to explain high pressure over here. What would that argument be? Something that we discussed in lecture number 2, probably in lecture number 1 as well. This is warm air, this is cold air, relative to each other. In which air pressure decreases with height faster? In warm air or cold air? If you have 2 air columns in cold air, so at the height, you will have higher pressure in warm air. You remember we discussed it. Because here the pressure is decreasing with height slower than in the adjacent column of air. And this is warm because of this huge amount of latent heat that is released from condensation. So you get actually low pressure over here. Again, if somebody asks you, where is this high pressure with respect to this low pressure? No, this pressure is lower than here. Okay, but this high pressure is with respect to the adjacent atmosphere. Okay, and you have some sort of completion of this circulation. Okay, so you see, the more condensation you have and the deeper these clouds, the stronger the convection. But the stronger the convection, the lower the pressure in the center. Namely, you can also say higher the divergence over here. That means higher convergence close to the surface. Convergence, divergence, we discussed in lecture number 2. And you couple that with all this is about the ocean. As the winds are spiraling in, you know that wind is promoting evaporation. So if you have calm weather, you have some level of evaporation. But if you have winds, evaporation is promoted. It's just like when you try to cool down your coffee. Beautiful. By blow. By the way, you know when you try to cool liquid, you shouldn't blow into it. You should blow on the side. That's because I can. See, if you have liquid, what do you do when you do something? When you try to cool your water? Somewhat related to hurricanes. You see this, you have some molecules here in liquid, and these molecules evaporate. But I mean, there is no turbulence here, so they just hover here, and they may be diffused through molecular diffusion. So when you blow, you remove these, and then the new one can evaporate. Because when this one evaporates, there is also a probability that can be calculated that it will go back to the liquid. So when you blow the side, you actually remove this moist air, and the new one can evaporate. Compare if you blow down, and I mean, still, you will remove it in this fashion, but it's much more efficient doing it that. If you remember everything from science storms, it should be how to cool properly a cup of tea. But at the end of the day, something similar happens in hurricanes. Because you see, you have these winds, you have evaporation of water vapor, evaporation of liquid water, and these winds are bringing it here, which means evaporation is still supported. And water is very hot over the depth of 50-60 meters, so there is a lot of potential for evaporation. Because also you have to know if this is the surface of the water and you know it, you live here next to the water. When winds are strong, you get choppy ocean, so you get a lot of mixing. So if only surface is hot and you mix water, it will be not so hot. But if you have hot water in first 50-60 meters, even after mixing, you still get warm water. That's why hurricanes don't form here in mid latitude, because water is not hot. And even if it is, it's not hot enough over sufficiently deep. Does this make sense? Now, going back to this figure, you have this cloud, here is high pressure, you have some spreading. Now, this often results in formation, because again, just like you remember in squall lines, this does not go directly horizontal, it can go like this. So you get some cloud that develops like so. And you get some other cloud here that develops like so. Now, it is very difficult to predict. And it's not even that important, but somewhere here you will also have downdraft. Somewhere here you have some precipitation and downdraft. This downdraft falls into the updraft and is brought back. But then some other cell gets initiated here. So this cell will also have some updraft and downdraft. and maybe another cell will be initiated here. So if you look into hurricane in these pictures, you see, I will plot a nicer picture now. Here is the surface of the water. Here is before the formation of the eye. I'll talk about formation of the eye later. But here is central cloud that has spread like so. Here is perhaps another cloud, and here is third cloud. Here you have strong updrafts. Updrafts are stronger as you are moving towards the center. And then the history repeats on the other side, with clouds being smaller and smaller as you move radially out. Here you have some downdrafts. Here you have strong updrafts. Now, I cannot tell you, if this downdraft will be 12.7 kilometers or 30 kilometers. It depends on the overall dynamics of this system. But usually, if you would take cross-section, vertical cross-section, ZX, let's say, of a hurricane, you get this. I didn't include because I'm not, you can now Google hurricanes and find many beautiful pictures. And if you do Google hurricane radar picture, you will get something like this. High regions of intensity intertwined with low regions of intensity and so on. Radar backscattering. Yes.
I have a question.
Yeah.
In this case, are important relative winds?
Relative winds. Not so much in this particular case, because you have one big inflow towards the center of hurricane. And of course, hurricane is moving in some direction. So if you are analyzing, let's now look from y-x, okay? Hurricane is moving in this direction, let's say. This is the circulation. And let's say the system is moving in this direction. Then, of course, the winds that you observe on this side of a hurricane are larger than winds that you observe on this side of a hurricane, because these winds couple with translation. That can be non-negligible, okay? But in principle, the storm relative winds in the case of hurricane are not as important in the case of as in the case of isolated thunderstorm or systems of thunderstorm, because in those cases you have very strong fronts that are basically gust fronts that we discussed, that are responsible for driving inflow up. So in the case of thunderstorm, you have this gust front, and then you have updraft going up the gust front. And now relative velocity of this updraft with the velocity of spread and the whole cloud motion play important role. But here, you see, the source of cloud is this. The source of these clouds is just moisture. As long as the water is hot and evaporation is therefore promoted, you will have very strong hurricane. That's why when the hurricane goes over land, which is called landfall, when it reaches land, it immediately starts diminishing. For two reasons. Reason number one, roughness increases. But reason number two, more importantly, there is no more source of water vapor, and the hurricane starts dying off. Okay?
Okay.
Any other question? Any other question from online folks? Okay. Is this clear, this conceptual model? And is it clear how, if somebody would tell you, this is technical wording, atmospheric science, that mid-latitude cyclones are cold core cyclones and hurricanes are warm core cyclones, do you see how that makes sense? because you have this very warm core associated with this very strong release of latent heat. But you remember that in extratropical cyclone or mid-latitude cyclone, the core was actually located in the cold pool. Okay. And what is driving convection is actually that divergence at higher elevation associated with jet stream and so on. So that's it. And these are vertical systems. These are vertical systems. You remember the cyclone was inclined system. Again, associated with the position of the jet stream and the frontal perturbation of the surface. You have to study that if you forgot. Now, another reason in this case why low wind shear is important is in the case of mid-latitude storms, as we saw, wind shear actually tends to organize storms because storms depend on relative velocity between storm and the surrounding air, surrounding atmosphere. But in the case of hurricanes, that's not so important. What is important, I'm sorry, what is important in the case of hurricanes is just evaporation and condensation of water. Now, I will just draw this typical figure that people draw. If this is the surface of the ocean, and you have idealized cloud that looks like this, of course, clouds don't look like that, but you, as we said in the very first lecture, when you make a model of some parcel of air, you can make it quite often or to be any way you want. You see, this cloud is condensation, so it's a release of latent heat, means warm, means low pressure at the surface. What is the area that this cloud occupies? If the sun is here, the shadow would be this. So the low pressure is the width of this cloud. But if you have strong shear, and we saw that in multi-cell thunderstorms, then the top of the cloud might be like so. So this is weak shear. Again, I always pull up a little bit of change in wind, so you don't think it's absolutely constant. But this is very strong shear. Again, this is cloud. Now, I didn't do a good job, but area, like this area, is the same maybe as this area of parallelepiped. And beneath, you will have low pressure. But is it going to be lower? Is it going to be as low as here? No, because this cloud is now, this is area A1, this is area A2, clearly larger, which means that the pressure drop here is smaller than the pressure drop there. That's why in the case of hurricanes, it's actually important to have the wind shear quite low, especially at high elevations, because you don't want you want clouds to be vertical so that the pressure drop is concentrated over smaller region. And that this is just 12 hours teaching. But if you study El Nino, La Nina, these are now popular topics. During El Nino, wind shear is higher, at least in Atlantic, and you have less hurricanes than during normal season or okay.
But during this period, also the water is not warmer.
During the El Nino, can you say?
Yeah.
Yes, but that's water in the Pacific, not Atlantic. I don't know, but so people notice that correlation as well. Just for you. This is South America. El Nino means warm water over here, right? But this Pacific Atlantic is because you have very cold water over here. And that cold water is actually very cold. And that's normal condition. Or La Nina means it's crazy cold. El Nino means reversal. I could now talk about these, but I don't have time. Any question from online audience? Oh, it's 4. So it's time for break. Okay, then we continue at 4:15. I will pause this recording. Resume. But in this second hour, I want to talk a little bit how we get these initial clouds that serve as a seed for further development of the tropical storm and maybe become a hurricane later. I want to talk about storm surge and formation of the eye of the hurricane. Most hurricanes in Atlantic form as a disturbance of the so-called easterly waves. Now I try to explain that without using fancy slides. Somewhere here is Africa. As you can see, for me, all continents look like this. This is a very common theme, okay? Somewhere here is Africa, and here are the Azore Islands, Sao Tome and Principe, Saint Thomas and Principe, so some small islands, I don't know exactly, are here. And here we have, here is Atlantic, here is land. Ocean, land, and particularly Atlantic Ocean. Here is high pressure system. The existence of this high pressure system is related to the general circulation of the atmosphere, which I didn't talk in this course, but this is permanent high pressure system situated in the Azores. And the circulation, as you know, in high pressure system in the northern hemisphere is clockwise, anticyclonic. And we are north of equator, 10 or so degrees. Okay, so we are here not very close to the equator. Now, this is uniformly ocean, this is land, piece of land. And you see these winds that cross the land get disturbed for various reasons. One of the reasons is just change of roughness between ocean and the land. Another reason, there are Atlas Mountains over here. Third reason is, in addition to mountains, this is also, there is a lot of vegetation, well, there is more vegetation than in Sahara Desert, so you get temperature differences. You have Sahara region over here that is bordering Sahel region, how they call it, that is bordering Sahara. So again, big temperature differences. So these winds that are blowing across northwest Africa get perturbed by these temperature and landscape differences. And quite often, they don't end up like that, leaving the island. But you have a formation of a disturbance that might look like that. Now, this is, as you can see, a wave. This is in horizontal direction. So you get a wave, and these waves are traveling towards the west. That's why they are called easterly waves, because they come from east and travel to west. And they travel in that direction because they are caught in this high pressure system circulation, which is anti-clockwise, which is clockwise in the northern hemisphere. Okay? Now, you see, if I take axis of this, this is called now pressure trough, because low pressure trough, I think it's spelled like, but I might be wrong. Maybe somebody has better English than me. I think it's spelled like this. this low pressure trough is pointing towards high pressure. It looks like that. And this is the axis of this trough. Now, if I zoom in over here, it might look like that. Let's zoom in on this region over here. And this is the axis of that trough. And the flow is clearly like so. Where do you have convergence? Where do you have divergence in this system? If this is the axis, are you going to have convergence here or here? Or in other words, are you going to have divergence here or here?
Convergence on the right, convergence on the
Here
left.
is convergence. Here is divergence. Right? There are a few ways to explain it. One way is, again, you have straight isobars here, you have current isobars here. The pressure gradient force is pointing towards the low pressure. The Coriolis force and the centrifugal force here are pointing out. Because two forces are opposing pressure gradient force, you have weak winds here. So strong winds become weak winds, that means convergence. Or weak winds become strong winds, that means divergence. Exactly what we discussed in the case of extratropical cyclones, but over there, everything was in the other direction. Okay. Another way, another contributing factor, rather in this case, you see how I plotted this here, because not you have a wave that forms. Perhaps this one is undisturbed, this pressure surface, and you know that winds follow pressure. So you see, over here you have convergence of winds in a way that this wind is colliding, so to speak, with that wind. And here you have divergence of winds. Do you see that? Something similar, but completely not related to this, happens if you have a lake and you have winds approaching the lake, and you assume all winds are the same everywhere, so it's uniform surface, but lake is water. So over a lake, wind speed is higher because roughness is lower. So Coriolis force tends to deflect these winds like so. Where do you have convergence? It's clear that you have convergence here, and you have divergence over here. Is that clear? Where would you expect clouds? Here, or even here. Here you also have divergence because strong winds become weak winds. And I mean, here it's not the same, but you can see the same schematic, so to speak, similar. So you get convergence on the easterly part of the trough and divergence on the westerly part of the trough. Now, convergence means what? Well, I mean, you have to know this by now. Convergence in the vertical direction, if this is height, means that you will have convection. And then that convection spreads. So you got, and again, we are assuming the ocean is very warm. What's the name? Air is full of water vapor. So you start developing these first storms. And if you have enough storms over here, and they keep propagating, they propagate to the west, more and more develop, they start going together. The more of them joins, the lower the pressure, and you start having this cycle that I explained in the previous question. Is that clear how you can get a seed of storms kind of out of nowhere? Now, research suggests that approximately 60% of hurricanes in this region forms like that. But over 80% of the strongest of strong hurricanes, and these are SS3 or higher, Saffir-Simpson scale 3 or higher, over 80% of these hurricanes form like that. So the strongest hurricanes tend to form in this way that I explained here. Okay? Is that clear? Any questions online? Now, the question is also, how do you get some other ways of hurricanes forming? Because this is approximately 60%. And this is a little bit unique to Atlantic Ocean and position of Africa. Sometimes you get hurricanes by, what is this? Yes, cold front descending from mid-latitudes all the way to the tropics. And you know that ahead of cold front, well, along the whole 1, 2, 3, along the cold front, or even ahead of the cold front, you can have thunderstorms. When these thunderstorms reach tropics, again, they can organize, initiate that closed cycle that leads to hurricanes. In 2002, you can check online famous Hurricane Kai, which I probably mispronounced, miswrote here, but you will see Hurricane Kai in 2002 forming on the due to the effect of thunderstorms that descended with cold front. You can see cold front being south east of the United States of America. Okay, so that can happen in other parts of the world. Fronts are not exclusive for North America, so that can happen in Pacific as well. And there is a third reason. You can get storms that organize clusters and start developing a hurricane. And that one is very, very simple to explain if you know general circulation of the atmosphere, okay? You see, if you assume that Earth is perfectly symmetric to incoming solar radiation, I'm not going to explain the entire general circulation of the atmosphere, that's a lecture. But this is North Pole, this is South Pole, this is equator. Okay? The strongest, so sun is shining, the strongest radiation, the strongest amount of heat that we get is along the equator. So the strongest convection is along the equator. You have very strong clouds, vertically developed clouds for there. Now these clouds hit tropopods, they spread, the air, sorry, spreads, and then you have descending here. Here are the regions of high pressure, here are the regions of low pressure. Subtropical regions are high pressure regions, equatorial regions are low pressure regions. Because of the amount of solar radiation that we get from the sun that is dominant in this region over here. Azores anticyclone is one of these high pressure regions in subtropical regions. You see, you have already storms that develop here. These are storms. But they are developed along the equator. And you know, as I just said, there is no Coriolis force along the equator. So they cannot become hurricanes. But it turns out that this zone is not actually equator. It is typically around 5 degrees north of equator. And that's already not equator. And that zone of low pressure system is not like this, but it also sometimes, you know, has ripples. Like so. So you can have storms, or this is called intertropical convergence zone. That this intertropical convergence zone can be north enough. And it's always or almost always associated with deep convection, and these clouds can also result in formation of hurricanes. Our question, you see? Look, this is called Hardwick 7. Hardwick 7, doesn't matter. Parcel of air goes up, then goes towards the north, then sinks in subtropical regions, and then returns to the equator. Let's examine this wind over here. Here is approximately equator, 0 degrees. This is actually, I just want to test your knowledge now of what we learned. Here is 0 degrees. Here are subtropical regions, high pressure. Here are low pressure, high pressure. Okay? And parcel of air starts moving down. How is it going to end up here? Is it going to end up straight down or in some other? Exactly, it's going to curve like that. Why? Because of the Coriolis force. It starts smooth, pressure gradient force is always the same, from high to low. This is northern hemisphere, it turns to the right due to the Coriolis force. Another guy from southern hemisphere, because this is also high pressure region, starts moving towards the low pressure, but it ends up like that, because the Coriolis force is turning to the left. And you have these winds, you see, that blow like that. These are called trade winds. Trade winds are one of the most persistent winds in our atmosphere. Mean wind speeds are about 5 to 7 meters per second. Not very strong, but very persistent. So you can also see that these winds converge. And when they converge, you get convection. Is that clear? That's this convection over here. But this is not generally at 0 degrees, but a little bit north. And a little bit north means sometimes these storms can also organize into hurricanes. So these would be three main ways how you initially get clouds to develop into hurricanes. Is that clear? Yes. Also, I wanted for the last two lectures to say something that I always forget. When it comes to literature that I provide, the slide says, title of the slide, supplementary literature. So it doesn't mean you have to know everything. You need to know what I'm talking about here. So of course, in those books and chapters, there is much more. If you want to know much more, I'll be very happy. But you don't need to know for this exam all these additional things. You should focus on what we are discussing in lectures, okay? So you don't have to think you have to start now, know all these chapters and okay, any questions? Online or here in person? So now I will rather quickly talk about the formation of the eye of a cyclone, of a tropical cyclone or hurricane. So here is the surface of an ocean. Here is height Z. And as I said, originally, I said you have strong inflow towards the center because over here you have low pressure. And then that inflow goes up. But I hope you can imagine, and not just imagine, but kind of visual, that the inflow is not going radially in, because we have requirement of the Coriolis force, so it is spiraling in. The flow is spiraling in, like so, in. Right? So if that is the case, what would be perhaps more appropriate way of plotting this is, I don't know, I pick a parcel of air from here. It will really be lifted like so, in a spiral way up, okay? So, and I don't know, some other one from here, perhaps like that. So you get spiraling of air going up. Now, in the center of the spiral, you have very low pressure. One of the lowest pressures in hurricanes was at 800 something, 70, or so I forgot, millibar. So that's extremely low pressure. Here you have, this is the wall of the cyclone. Here you have very strong clouds, and here you have very strong clouds. Now you see this air that exits here in the wall region. This is called eye wall. These clouds. This air that exits here, indeed, as I plotted, some of it goes out and then forms this cap of clouds. Is that clear? So this air that exits goes like here. But some of it also spirals back in. Okay? And the air that spirals back in is adiabatically warm as it is going down, so it starts destroying the clouds that maybe even form over here. So as the time is progressing, no, I know you have maybe many questions about what I just said. I'll address them soon in one sentence with the answer I don't know. But in principle, you start with a center that has a cloud. And this is at time t equals 0. So the air is spiraling in like so. But as the system is deepening, the low pressure system is becoming lower and lower, and spiraling is getting higher and higher. And you have air spiraling in such a strong way that in the center of the spiral, you have so low pressure that some of the air returns in, starts descending down. And of course, that means in the next moment in time, this cloud, because the air is spiraling in, this cloud is diminishing. In time t2, this cloud is becoming even weaker because part of the air in the eye wall region returns. It returns to the center. People usually plot it like this. They put eye wall clouds over here, and they tell you there is extremely strong updraft that spreads like so, but some of it also returns towards the center. And in the center, it sinks, establishing this circulation. You will see something like this, in fact, develops in tornadoes. In many tornadoes, in the center, you don't have updraft, but rather downdraft. This is called two-cell tornado. Because the central pressure is so low, thanks to the very high swirl, that the swirling that is displayed, that the swirling that has certain diameter, air that is going up in that swirl, part of it goes back. Now, you might say, how much is, this is what I will say, I don't know. How much air is going in? When is the eye going to form? Because not always we have the eye. The answer is I don't know. When I joined McGill, because there is still research on this, it's not quite clear of the mechanism of eye formation. When I joined McGill, one of the first PhD defenses that I attended, so that was 3-4 years ago, a student was doing numerical modeling of the formation of the eye in the cycle. So these are all plausible mechanisms, but there are unknowns that are still in this whole thing. But conceptually, is this at least a little bit clear? Again, you have air that is swirling in, going up. And I'm not going to overwhelm the figure, but you have another one, let's say from here. Because this vortex is so strong, you have very low pressure developing in the middle, and some of the air is returned, some of the air goes back. From this side, some other air returned, and of course you have convergence that results in sinking. And as we studied in the lecture number 1, when you have sinking, you cannot have clouds. If you have clouds, they start being destroyed. But when this convergence is strong enough to destroy clouds, under which condition this whole thing will form in that way, we don't know exactly. Okay? Just like we don't know for real tornadoes in nature, when they will develop something like this, and when they will have updraft in the middle, which I will talk when I talk about tornadoes. Okay? Now research, research, some satellite images show that even some extratropical cyclones develop eye, which is completely not clear how that happened. But you have a few images where at least there is some indication of the eye in the center of extratropical cyclone. Yes.
So the hazard of the high wind speed is due to the spinning or to the downdraft?
Spinning.
So the downdraft is not strong enough.
No, there are downdrafts as well, for sure. Whenever you have precipitation, you have downdraft. But in the case of hurricanes, it's really this parcel of air from here is the center of low pressure. Oh, I should fail with that if I did it like this. That swirls in like so. These are high intensity winds close to the surface. And the maximum is, I don't know, somewhere, let's say here. These are damaging winds, usually. And you can also see, because this is now hundreds of kilometers, 1,000 kilometers, you can see why people approximate these winds as straight line winds. Because yes, there is curvature, but your house here is really so small that you can approximate these winds as straight line winds, which is not the case in downbursts and tornadoes. In downbursts there are also straight line winds, but not straight line in terms of vertical. Yes.
So the profile is similar to the extratropical.
That's correct. Profile is typically logarithmic. So winds in hurricanes, quite often, not always, it's never like this, when you measure, you get some crazy, but quite often it's logarithmic profile or log law. Where here is mean wind, here is height is that. And that's what they replicate in wind tunnels when they test for hurricanes. Now, because at the end of the day, hurricane is also a cluster of thunderstorms. Some of these thunderstorms sometimes form tornadoes.
Doctor.
But these tornadoes are not as strong
Hi, Doctor.
ones that are formed with supercells. You remember the supercell clouds? They are the strongest tornadoes. Because again, we will see in next lecture that for formation of tornado, you need both updraft and downdraft. And as you said, here you also have some downdrafts and you have updrafts. So it will be clearer in the next lecture. You might get a tornado, but it's never never. It's rarely as strong as tornadoes that form from isolated supercell clouds. This is also one of the drawbacks of Saffir-Simpson scale, because it rates hurricanes only on wind speed, but it neglects if there was tornado, it neglects if there was, although there is rarely hail, but if there is hail, it neglects that. It neglects damage caused by flooding, because some hurricanes have huge storm surges that I will talk about now, and that is not taken into account. Only wind is taken into account.
Hi, Doctor. I have a question.
Yes.
I need to know where is the most damaged location? Is the center of hurricane or at the edge of hurricane?
In between. The most damaging winds are in the wall of the hurricane, the eye wall. So if the eye, as I said, is usually 50, 60, 70 kilometers in diameter, then the eye wall is, let's say, 100 kilometers or so from the center. But
So
that
the
depends.
force, yeah, the force will be the centrifugal force that will affect the structures in this area.
The winds that you sometimes can approximate as gradient winds are, yes, balance between pressure gradient force, Coriolis force, and centrifugal force.
Okay.
So the winds are basically tangential velocity that is so this is wind in a hurricane. You have low pressure in the center, so these are damaging wind. Velocity, if this is a streamline, then velocity is like so. That close to the surface has radial component in because of friction and has very strong tangential component that is tangent to the streamline.
Okay, thank you.
Okay,
Thank you.
you're welcome. Any other question? Okay. Now, last 10 minutes, I would like to talk about storm surge and then show you that one slide that I find very nice. So as I said, storm surge is responsible for over, 80, 90, some research suggests, percent of deaths associated with hurricanes. And storm surge is a big tide associated with hurricane, and it's particularly devastating when it couples with natural, did I say low tide? High tide. It's particularly damaging when it couples with high tide during the day in that region of the ocean. So if you have a surface of the ocean, I'll make it flat, like so. This is again height Z, and here are those storms. Now we should be familiar with this picture of the hurricane. This is the eye wall, and this is the surface of the ocean. Let me display the surface of the ocean down. Let's say here is the surface of the ocean. So you quite often the surface of the ocean doesn't look like that, but it looks like there is a bulge close to the eye of a hurricane. Okay, and then if the hurricane is moving in this direction, and you live somewhere here, and you decide not to move, you probably die. That's because if you are on a beach and you see a hurricane approaching, or they told you hurricane is approaching, the last place where you should be is a beach or some low land. Now, what is causing this high dome of water, or dome of water that is following hurricanes? Well, you can see that these winds that are spiraling in are pushing water towards the center of the hurricane. Now, let's assume that over here, this is now the bottom of the ocean. Okay, so over here you have land, and over here this is now ocean. Okay, and you have this bound that is forming that maybe is just a few meters in deep ocean. But as this is approaching the shore, the depth of the ocean is decreasing, and this is growing. So you end up with much bigger dome of water over here. And that is moving with the hurricane towards the land. And then, of course, if here is house, that can be severely damaged or flooded, or if you stay there, because these storm surges, as you saw, can be in those slides 5 to 7 meters in extreme case above the mean sea level prior to the storm. So you see the small one deep in the ocean, far from the shore, can become quite a big one when you get close to the shore, because the depth of the ocean decreases, and all this water that is pushed from these winds towards the center of the hurricane accumulates over here, creating big dome. So that's one reason for this surge. So, and that's the dominant reason. So that's the winds that are pushing water towards the center of the hurricane and then towards the land as the hurricane is approaching the land. Another reason, but approximately only 5–10% of this bulge is associated again with very low pressure in the center of the hurricane. Just like when you have a straw and you drink water from a cup, you drink it thanks to the low pressure in your lungs. The same is here, you have very low pressure that lifts the water. And you can do calculation that for every hectopascal, namely I told you hectopascal in millibar, you get a raise of sea level for about 1 centimeter. No, it's not much, but if you have a center of the storm that is 900 hectopascals and 1000 hectopascals is somewhere far away, you get 1 meter raise just because of pressure deficit. And then that pressure deficit, when coupled with very strong winds, you get 4, 5, 6 meter storm surge. Okay. Now I would like to talk a little bit at the end. What are other contributing factors for storm surge? So this is the dominant, okay? Winds that are moving water towards the center of a hurricane and then towards the shore as the hurricane is approaching the shore. Now, if you have, I exhausted all of it. If you have a shore that looks like this, compare the one that looks like that, then this one is much worse. The water in this case can penetrate much deeper than in this case. Okay? But there are all kinds of engineering things, how to protect the shore, which I don't expert in. How to protect shore from hurricanes, how to build certain structures to break the waves and reduce the penetration depth of the big wave inland. One of them is to make steeper coasts. Another thing is, if you have land over here, namely continent, and hurricane is approaching like so, then usually the biggest storm surge is on this side of the hurricane, where what we discussed, where you have stronger winds than here, because here tangential velocity of hurricane is subtracted from the motion, whereas here they are added. So usually you get in this region the largest surge. Also, the surge is much bigger when the hurricane is approaching shore 90 degrees or so, than if the hurricane is approaching under some angle, like this. This is worst case than this. Now, in terms of the size of a hurricane, smaller hurricanes can create very high, actually, storm surge, but localized. Whereas big one, they can also create very high. They're strong, but it's usually spread over a larger area, and therefore more people can be affected by that storm surge. And it also, there is also some correlation between motion velocity of a hurricane and storm surge. If hurricane is advancing fast, Then storm surge can be very impulsive, but last not so long. Whereas if it is slow moving hurricane, the storm surge can last for quite some time, and maybe, you know, if you have two take, you have option to have the one that lasts for a few days, but it's just boring, or the one that lasts not, well, this was horrible analogy, but actually you get the point, okay? I tried to go in some direction, but I failed miserably. But you get the point, okay? Huh? Yes. What else should I say about this? Any questions? Yes.
Are there any models that try to
Yes.
explain the trajectory of the hurricanes and the
Yes.
velocity of storms?
Yes. So people run numerical. Now there are some numerical models specialized in hurricanes where the, you know, like you have fine grid that is following hurricane. So that you constantly resolve hurricane in a much better way. And then people run ensemble models because none of the models is perfect. So you run 20 models, either different models or same models with different initial conditions. And then you get, so let's say here is time t equals 0. You know that hurricane is here. That's where you measure it. And then maybe this is mean trajectory of a hurricane from 20 different simulations. These are numerical weather prediction simulations. These are not CFD that Josip is driving in. These are numerical weather prediction. But this is t equals 0. This is, let's say, 24 hours later. And this is t0 plus 48 hours. So you get mean trajectory and you get some spread that, of course, always grows with time. Sometimes they publish it like this, sometimes they publish it like called spaghetti diagram, where you have all these different trajectories from different models and then mean trajectory. So you predict where the hurricane will go.
But they start from the same initial condition or from
No, this is same initial location. You know that you're not missing location. You have now some position, but you change temperature profile, you are uncertain. You change wind speed profile, you change moisture content in the atmosphere, and then you integrate. So you start from where the hurricane is, but you change initial conditions in terms of atmospheric variables in the model.
because these are the
Because they're uncertain. Yeah. And then you get many predictions. Now you can predict the path of maximum winds, SWAT area, what is called, you know, area of damaging winds or center of the cyclone, tropical cyclone. So, and then this is updated as the time is progressing.
but there is no physical model that explains, for example, why the velocity or the hurricane should be like this, not numerical, but let's say some physical.
No, there is, because you can also monitor what they do. This is underneath sea, so you know sea surface temperature. So if you have even warmer ocean over here compared to here, you can expect that the hurricane will strengthen over here. If it is approaching land, again, you know now, let's say roughness, length, models can predict what will be the weakening. So
It depends on the water temperature.
yes, that's the dominant. For hurricanes, sea surface temperature is the dominant driving mechanism. Okay. Let me show you the last slide. Speaking of sea surface temperature. So I need to go back to, can you turn on the, do you have a remote, Massimiliano? Do you have a remote? Turn on the, so share screen. Share. Okay. This is a mid-latitude cyclone. Very slow, it's windows. So very bad. But well. There we go. Can people online, did I share screen properly? I think I did. So you see, here is Hurricane Katrina in 2005, August 2005. You saw photographs from that hurricane. This is sea surface temperature. So it was about 30 degrees and it was rising and it reached almost 31, 30.8. I might say this is not much, but for a huge ocean to increase temperature for 1 degree, it's enormous. And then Hurricane Katrina hit. And look, the drop in sea surface temperature during just 4 days, okay? Between 26 August and 1st of September. Look, temperature dropped for more than 1 degree Celsius. And this is estimated here. This is 4-day drop of temperature. This is where Hurricane Katrina passed. This is based on satellite measurements of sea surface temperature. And then soon after that, another Hurricane Rita hit the same location. So you can see that Hurricane Katrina, imagine temperature of the sea 30 degrees. I mean, that's 10 degrees more than here from in the Mediterranean in general. But then temperature was still very high, about 29 degrees, 29, 30 degrees Celsius. And then another hurricane hit that passed here, 4-day temperature drop. Look how significant temperature of the ocean dropped after hurricane passed. And then again, time passes, sun shines, water gets warmer. Now, it's not shown here. Later in October, there was yet another hurricane because temperature of the water kept increasing, okay? So I find this figure just amazing because you see, hurricanes are necessary. They will always happen. They are like reliefs of energy from the ocean. Energy in the ocean in terms of internal heat is accumulating hurricanes releases. And then you still have, in this case, another hurricane hits. So hurricanes are inevitable in this point because they cool the oceans. How do they cool the oceans? Well, all that evaporation cools the ocean, but warms the atmosphere. Warms the atmosphere because that water that evaporated condenses in clouds, and condensation releases heat, whereas the evaporation takes heat from who? From ocean. Okay? And these are two exact questions. Probably the first one is a little bit trickier than the second one, but so is life as well. So, any questions? Any questions from online people? No? Okay, then I don't know exactly the date of the next lecture, but in about 10 days or so. I'm looking forward to see you all again when we will talk about hazards associated with various storms. I mean, that lecture should be 7 hours because there are so many hazards I would like to talk about, but we only have 2 hours. So I will have to condense it, okay? See you everybody next time. Have a good rest of the week.
Thank you, Professor. See you again.
Thank you.
Goodbye.
Bye bye.